The graph of a function f with domain 0 to 4 is shown in the figure. Sketch the graph of the given function f of negative 1/2 x. Well, let's actually give a name to that transformed function. Let's say that g of x is computed by taking f and evaluating it at negative 1/2 of x. I'm going to extend the graph that we were given so that we can use that to sketch the resulting graph of g, the transformed function. Notice a couple of things are going on here. First, we have f evaluated at a modification of the argument of itself. So we have a negative 1/2 times the x coordinate. The negative sign is going to replace any x value that was positive with a negative x value. So we should expect that the resulting transformed graph has been reflected across the y-axis. That's because, again, if we have positive x values that we input into g, those are going to be multiplied by a negative, and they're going to turn into negative values to be fed into the f function. And likewise, if we had negative values to feed into g, then those values would turn into positive inputs into f. So the x-axis is effectively reversed whenever we have a negative multiplier inside the argument of the function. Also, because the value of the multiplier is between 0 and 1 in absolute value, that is, it's just a fractional value, that's going to have the effect of stretching out the shape of the graph in the horizontal direction. To see that, we can always plug in a couple of points and get a sense of how things are changing. Let's try to work out the value of g of 4. Notice, though, if we try this, we're going to have to do f of negative 1/2 times 4. That's f of negative 2. And f has a domain that only ranges from 0 to 4, so we have no way to evaluate f at negative 2. You can see if we count to negative 2, there's no function f plotted there. So we actually cannot evaluate g of 4. 4 is not in the domain of g. Let's try g of negative 4. Well, that would be f of negative 1/2 times negative 4. That's f of 2. F of 2 can be evaluated from the given information about f. We see that f of 2 is 0. So that tells us that in terms of ordered pairs, g takes the number negative 4 and turns it into 0, and one of the points on the graph of g will be the point negative 4, 0. And we can plot that here. Let's see what happens if we look at g of negative 8. That's f of negative 1/2 times negative 8, which is f of 4. f of 4, we can see from the original figure, is equal to 3. Over here on the y-axis we have 3 corresponding to the point above x equals 4. So f of 4 is 3. That means that g of negative 8 is equal to 3, and we need to extend the graph a bit further. There's 5, 6, 7, and negative 8, and we should plot a point up at positive 3 on the graph of g. This is the point negative 8, 3 on the graph of g. Maybe one more point is useful. Let's graph g of 0. That would be f of negative 1/2 times 0, which is f of 0. And from the graph we can see that f's value at 0 is also 3. And that means that another ordered pair on the graph of g is 0, 3. And we can plot that point here. That gives me a good enough picture of what the graph of g is going to look like. It's going to be the mirror image of the graph of f that we started with. And remember, we said that when we have a negative multiplier in the argument, that's going to be a mirror image across the y-axis, actually a flip about the y-axis. And it's also going to be stretched out by a factor of 2 because the absolute value of that multiplier was between 0 and 1. So this is the graph of the shifted or transformed function f of negative 1/2 x.